Additionally, remember that we can do very sophisticated runtime documentation in Python. And that runtime documentation may be very helpful for our end users. When we talk about testing, we can talk about testing from a variety of different angles. We can talk about testing that occurs as a discrete process prior to deploying some code. And we can talk about testing that occurs when that code starts up. That might be a constructive notion of testing the state of the libraries or the imports that you have. We can even talk about tests that occur during the execution of the code itself. And remember, Python offers you a lot of really sophisticated ways to perform all of those different types of testing. And each one of these can also serve as documentation. For example, if you look at this code, you can almost immediately spot one thing that might be buggy about it. If this value is 0, we'll get a divide by 0 error. If this value is negative, we'll get a domain error. The math.square root won't allow us to take square roots of negative numbers. What that means is, if we're looking at the ny's of a sequence and we're looking at adjacent values, well, this is negative if each value is larger than the previous value. So if this is an increasing sequence, this will be negative and we'll get an error. One of the assumptions that we have here is that what was passed into this code was a monotonically non-increasing sequence. And looking at this code, you may not know, well, is that a fair assumption? Is that just something that we assume as a consequence of the way in which this code is eventually called on the data that's passed in? Is that something that is no big deal, or is that something that we have to keep track of? Well, in this sense, we can use simple mechanisms like asserts, which, as you know, if we run our Python code with the -O flag, asserts and statically determinable if clauses will be elided from the code. They will be completely removed from the code. So for example, if I say assert all of the values in this sequence are monotonically non-increasing, that is to say they're decreasing or they stay the same, like this, well, if I run this with just normal Python on, say, let's do 4, 3, 2, 1, everything works fine, and that check will be run. However, if I run this with Python-O, let's pull in our dist module to take a look, this assert will be completely removed from the source code. Here you can see it's quite a bit of source code here, but you can see here this is the ny's with the third argument. If I take out this -O flag, you'll see here is my check. Well, let's actually go up a little bit higher and figure out where that check is. Right here would be our check with the assertion. You can see the load assertion error right there. Similarly, if I do something like this using the debug built-in value, which is immutable, it cannot be changed, this entire if clause will be removed from the actual code that's run if I do a Python-O. So I can even do much more expensive things, like I could take a copy of this thing and say x's and x's copy equals that. I could, for example, islice this, which might mutate the thing that's being passed in. I can do all sorts of very expensive things which I don't necessarily want to do in production. And I can say this constitutes documentation that more or less has a certain guarantee of being up to date, because a comment can stay a comment that's wrong when there are code changes. But this, at some point somewhere, somebody's going to run it. They're going to see that something changed, and it's going to draw their attention to that. Now, with that said, I want to share with you the narrower focus that we are going to take. We're going to be talking about testing that's done as a deliberate, discrete action, typically after we make some change to some code prior to sharing that code with somebody else, prior to deploying it to production, or releasing a new version of some library. And we're going to do this using a library called Pytest. Pytest is actually fairly straightforward. You give it .py files with functions that are titled test underscore something. There are other discovery methods, but that's a typical discovery method. Inside the body of that function, you give it assert statements. Pytest will translate the AST for the Python code that you give it into something that'll give you some nice output, like the following, that says, well, this check failed, this is where it failed, this is what went wrong, and this is the summary of its usage. And so we'll focus on just that. Now, I want to talk about the nature of the tests that we might write. And so let's say we have some code, and the goal of that code is to clear out some data structure, maybe clear out a list. Now, this is pretty easy code. Here, we could do something like if this is a, actually, I think this should work on pretty much everything. So here, that works on a set. It works on a list. It works on a dictionary. But it's not really going to work on a tuple, so maybe we need to have just a little bit more behavior here. Here, we could say that this thing clears out the structure, or if it's immutable, returns it in place. So we could say something like if this instance, as a very, very simple simplification, here we just return that. Otherwise, we do that. And we say the anticipated usage is you always do a rebinding, even if it's the case that the thing was updated in place. How would we write a test for this? Well, one way we could write a test for this is we just do very simply. We give it some example data. For example, 1, 2, 3. We call clear on this in the way that it's intended to be called, and then we assert the state of this. We could say the length of this is equal to 0. If in case we're worried about, for example, passing in an numpy and d array and getting the truth value of an array with more than one element is ambiguous, use any or all type issue. Whatever the case may be, we could write a very simple test here. Note, there is something lurking behind this test. In the assert, we know what to assert. We know what the behavior of this clear function will be. We don't necessarily know how it's implemented. That may be something that we have to go looking at the source code to see. That may change over time, but we know that as a consequence of this clear function, whatever we get back should have no elements in it. We have a very clear sense of how do we determine what this thing does and whether this thing is working correctly. In a very similar sense, let's say we have a function like a sort. Here we have a very simple implementation of a bubble sort, and if we wanted to test this thing, we could similarly say, okay, let's give it some dummy data. Let's do the bubble sort on this dummy data, and this is not an in-place sort, so here we go. Let's even just use the built-in sorted as a comparison, and let's assert x's is equal to y's. And again, if this sort is correct, then we should see that this just works. Of course, let's not pass in the x's there. And here we, of course, do need our nwise import. Here, let's do a from itertools import pairwise to pull this in very quickly. So there we go. Note, in this test, we also know what to check the results of this function against. We have an exact equal. We know that bubble sort is basically the exact same thing as sorted, except for the implementation detail of how it goes about doing that sorting. Now, obviously, the sorted has a key function parameter, and our bubble sort doesn't. That's another detail we can work with. But ultimately, we have what we might call an oracle. We have some out-of-band agent, something that is not present in the code itself that we wrote, this code for the bubble sort, that tells us whether the bubble sort is operating correctly or not. And in the case of the clear, well, we didn't really need an out-of-band agent. No matter how that code was written, we didn't need to compare it to something else, because it's always the case that it's just going to do the same thing. It's just going to always give you something with 0 length. But for the bubble sort, we might think, okay, we need to compare it against something else. Let's just compare it against an existing sort. We might even do this purely out of expedience, because of course, we could just hard code what the actual value looks like. But we might say, you know what, it's just a little bit easier for us to use the sorted built-in. That saves us a little bit of redundancy if we change what the test data looks like. Note, this is what we might call a expected versus actual test, where we can say the expected or the actual is what we get out of the thing that's under test, the FUT, the function under test, and the expected is what is provided to us by our oracle. Note, one of the most common oracles that we have is the human being who desk checks this. So in the absence of having this sorted implementation, well, it would be a human being that says, okay, just thinking through this, 3, 2, 1, we put it in sorted order, oh, that will be 1, 2, 3. The question is, what if we don't have an oracle? If we don't have some external body to tell us this thing is behaving correctly or this thing is behaving incorrectly, well, we're kind of stuck, in part because, think about it, if our oracle is a human being, then we're limited by what the human being can actually validate, and some functions that we might test will be very complicated, so we are reliant on the human being actually making sure that the code works. As a shortcut, we might capture the output of the code and then say, oh, we're fixing on that output of that code. But you can imagine with things like the imprecision and inexactness of floating point errors, that becomes very noisy very quickly. The exact output may be something where changes that we consider to be not particularly meaningful or material to our end users might cause changes in the test. So just doing a snapshot before and after is not the greatest test because it doesn't really check that the thing works. It only checks that the thing works like it used to work. But how do we know that it used to be correct in the first place? Similarly, if we are relying on a parallel implementation, that only really works in narrow circumstances where we're doing maybe some optimization work. Because if we were to try to apply the same idea to something like a very simple function that gives us values from the Fibonacci sequence, well, how do we actually write a test for this? Well, we could do something like this. We'll say A and B are 1 and 1. We might say, okay, here is our expected. That's an empty list. We'll say for whatever in range 10, expected, we'll put A and B into this as well. The expected appends whatever its last two values were summed up. And our actual is just the actual function we have. And maybe we'll islice this to, say, 10 elements. We could, of course, parameterize how many elements we're looking at here. That's a smaller detail. And we could say assert the actual equals the expected. But here's the problem. This is circular reasoning. This is, under the classical definition, what we call begging the question. We just wrote an implementation of the Fibonacci sequence. If we're so certain this is correct, why isn't this the code for the function in the first place? This test is like saying, test that the function gives us what the function gives us. It doesn't actually check anything. And we are oftentimes seduced into thinking we can come up with a parallel implementation, but if we had a parallel implementation, either one, we're doing double the work, or two, we are basically saying here's one that's guaranteed to be right and one that we're not certain if it's right, and we're using the one that we're not certain if it's right. And if you really think about it, how do we even know that this is correct? And so these kind of oracular testings leave us deeply, deeply, deeply wanting for something better. If we were to formalize how we might think about testing, what we might think is, if we're doing function level testing, unit testing as it were, we can think that some function has a domain. It has the inputs that we pass into it. And even when we're talking about things that are pure, things that are stateful, we could just consider the state of the world to be one of these inputs, the state of the global variables, the file system, all that. That's just one of the inputs. When we test, we're feeding in some inputs, and then we're looking at the outputs as a very simplified model. And if we think about it from that perspective, what we're going to say is, within the domain, within all of the possible inputs, there are certain particular input values that we have assessed might lead to output values that are not correct. That's what is considered to be a buggy piece of code. Our goal is to try and find those. And if we're writing tests of the form, okay, assert f of 1 equals whatever, assert f of 2 equals whatever, assert f of 3 equals whatever, all we're doing is taking little pot shots into what is likely to be a very large domain and saying, okay, I'll check this point, I'll check this point, I'll check this point. I don't think that's particularly scientific. Just because these 3 tests passed, who's to say that other tests didn't pass? Who's to say that f of 4 is completely erroneous? And so in truth, what we often try to do, especially when we come up with these individual examples, and also when we do things like property testing, is we're trying to take that input domain and we're trying to partition it. We're trying to say, here is the input domain. We're going to break it into parts, and we're going to say that for each partition, any example that we can pull from that partition is representative of the partition as a whole. That's why when you see some function that, for example, operates on a sequence, you might say, you know what, one partition is if the sequence is empty. One partition is if the sequence has 1 value. One partition is if the sequence has 3 values, but it doesn't really make sense for me to try 4, 5, 6, 7 values. All of those will be equivalent. The problem with setting these up in this fashion is we are deeply dependent on a human being being able to discover those partitions, and it's not certain that we can discover those partitions because in practice, what do we see when we run and discover code that has bugs in it? We discover, oh, we never considered that scenario. Let's add a test for it. Now, of course, if you discover a scenario that is erroneous, adding a test for it to lock in that the fix is there and that fix doesn't regress back to being broken later, That's a fine thing. But as a predicative value, you're basically relying on production to tell you something blew up, and then you after the fact to come in and to say, well, it blew up under these circumstances, we'll make sure it doesn't happen again. That's not particularly proactive. And so we want to see if we can discover better techniques.